I'm Barbara Stauffer, Chief of Community Programs at the Natural History Museum next door, and it's my pleasure to welcome you to tonight's After Hours program. So tonight's program is part of the Earth's Temperature, History, and Future Symposium. This is a 3-day event for teachers, journalists, researchers, and the public, focused on the important role that paleoclimate research plays in understanding and predicting climate change. And now, please join me in welcoming to the stage Kirk Johnson, the Sant Director of the National Museum of Natural History.
Thanks, Barbara, and hello, everyone. Welcome to the National Museum of American History. It's my really great pleasure to invite you here for this event, which in my mind kicks off the beginning of some amazing times at the Smithsonian. We've been working for well over a decade to produce this new phenomenal exhibit called Deep Time, which opens next year. And surrounding that is this halo of programming and research and symposia, educational preparation, various films, books, things that we're all putting towards this amazing opportunity we have here in the National Mall in Washington, D.C. to share the story of our planet with the people of our planet. And this place that you're on, the mall, gets millions of visitors a year. And this is where America comes to feel proud about itself, to understand how our government works. And the Smithsonian exists to increase and diffuse knowledge of all kinds. And tonight you're getting in for a tremendous treat. We've got a program for you tonight which I am really excited about because of the nature of the program and the nature of the people that are presenting the program. As you know, the Smithsonian doesn't charge for anything. We've watched museums in other countries that charge for admission and watch your admission drop off by 80%. So there's no demographic knife that separates people from the opportunity to see and learn about the natural world and the cultural world here at the Smithsonian. And obviously that takes help, not only from the federal government, but from philanthropists. And I'm really grateful tonight to recognize the gift of Roland and Deborah Sauerman, who are the supporters of this evening's program and the weekend, the whole symposium. So thanks, you guys. The Smithsonian's been around since 1846, but it opened the U.S. National Museum in 1881, and the first director, George Brown Goode, had this concept that museums were not only places where experts studied the natural world, but also places where the public was invited in to understand what the experts were figuring out. And today we continue that practice of collections surrounded by expertise, surrounded by visitors. And tonight we're launching this 3-day discussion of climate with two of the most amazing climate scientists I've ever met. And I know them both quasi-personally. I've met them several times, but I know them much more from reading their stuff and watching them over the last couple of decades. We'll first hear from Richard Alley, who's a professor of geosciences at Penn State University. Richard Alley was involved in coring the Greenland ice cap in the late 80s. He chaired a National Academy of Science panel that published an incredibly jarring results in 1993 that showed that even during the end of the last ice age, that the climate could change abruptly on a human time scale. You'd see abrupt climate change in 3 years. Before that, it was like, it happened a long time ago. It must take a long time to happen. You don't have to worry about it. But once he said you can change climate in 3 years, it sort of caught people's attention. It was the beginning of this awareness that climate was an issue of direct relevance to people on the planet today. He went on to do incredible communication. He served as a lead author on the 4th assessment of the Intergovernmental Panel on Climate Change. That was the one that got the Nobel Prize. And he has written a couple of really compelling books. His book, The 2-Mile Time Machine, is about coring Greenland and understanding how the core at Greenland captures the last 120,000 years of Earth's climate history. And his book, Earth, the Operator's Manual, something that everybody should read if you live on planet Earth. Andy Revkin from the New York Times, who's now at National Geographic and who's sitting right there, once described Richard Alley as a cross between Woody Allen and Carl Sagan. So you're in for some interesting joy coming up tonight with that one. Our second speaker is Gavin Schmidt. He's a climatologist, climate model, and director of NASA's Goddard Institute of Space Studies in New York. And he has been working with the climate models, not only for planet Earth, but for all other planets, and even planets we're just now discovering, to understand how planets work. So while Richard did the operator's manual for Earth, Gavin is working in the operator's manual for any other planet in the entire universe, which is quite amazing. In 2004, he was a co-founder of a website called realclimate.org. And if you have any interest in climate, as I did, and it was growing very strong in the late 80s, late 90s, realclimate.org was the go-to place if you weren't a climate scientist to understand what climate science was all about. It still exists now. We were just chatting about it before the event started, and he's saying, well, it's getting a little bit long on the tooth, but I still go back and check out realclimate.org. Or listen to his 2014 TED Talk, which has seen 1,179,000 views on the importance of climate modeling and how climate models help us understand planet Earth and help us understand climate. So after both of these guys talk, then Rachel Gross will come to the stage and moderate a conversation between them. Rachel is the editor of Smithsonian.com's science section, where she covers new discoveries in wildlife conservation, global climate change, and human evolution, with a goal of helping readers better understand the natural world. And she's worked for Wired Magazine and Slate before coming to the Smithsonian. And I think we're in for a really fun evening. And so without further ado, because I actually really think these two speakers are just the best thing ever, I'm going to get off the stage. So thank you.
It is fantastic to be here, and it's a little start on where we're going. So at any rate, thanks to Scott and Brian and their colleagues who set this up, to the Smithsonian, to the sponsors. Sharing the stage with Gavin and Rachel is going to be really fun. And thanks to you for coming. Your interest and your commitment to seeing what the Smithsonian is up to is really good. So thank you for that. I'm going to do climate history. That's our topic here. But we have to put this in a frame, I believe. And ultimately, when we talk climate in the US, we end up talking energy as well, and you can't not. All right, so we had a little snack before we came over here, and I grabbed a couple of the cookies. A human diet, we usually figure, is 2,000 calories per person per day. That's 100 watts. If you just burn that during a day, it's the equivalent of the light bulb. If I actually had to ride a bicycle to make the electricity, to make the light bulb, I would be out of breath, and that's sort of all I could do. But I don't. And I ride my bicycle a lot, but I didn't ride down here from Pennsylvania. We drove down. And if you take all the energy in the US economy and divide by the number of people and turn into these units, we are supported by more than 200,000 calories per person per day. It is as if each of us has more than 100 people to do our bidding. Serfs, right? Serf, cook for me. Serf, plow for me. Serf, pick up my car and run down the interstate at 70 miles an hour. Serfs can't do that, right? And it's about 83% fossil fuel right now. And this is unconditionally unsustainable. The fossil fuels accumulated over a few 100 million years. We are burning them over a few 100 years. We must change, right? Now, how good fossil fuel companies are at doing this, how well they have done what we ask them, is fantastic. All those coal trains are full of coal. It's stuff. And when you burn it, it's still stuff. And we can't see CO2, but it's real. And just for a scaling, you know what trash looks like. You've taken the trash out. You've been stuck behind the trash truck. In the US, per person per year, we throw away at the curb for the trash collector 1/2 ton. Each of us, 1/2 ton of trash. Our share of the CO2 from the US economy is 19 tons. 1/2 ton of trash, 19 tons of CO2. And this will change climate, and it will, okay? I mean, this is not something that you can get away from. Gavin's the expert, and I'm going to not try to step on his toes too much, but the physics are unequivocal. You can't put that kind of CO2 in the air and not have a warming influence. The data are very, very clear. It is warming. And in fact, when I was a student, the early models told us how it would warm and what the pattern would look like in summer and winter and north and south and land and ocean. That is happening. The models are successfully predictive as well as explanatory. They work, okay? And then history is the fourth one, and that's what I'm going to talk to you about today is history, okay? We put up a lot of CO2, we will change the climate. This is very, very high confidence. So far, the changes that have happened, if you're a poor person in a hot place, you're pretty unhappy. If you're a rich person in a cold place, you're not bothered too much yet. As the climate change gets bigger, it shifts more and more to losers and fewer winners. The costs go up faster than the temperature. As we move outside of our adaptive capacity, it gets expensive really fast. It goes from nuisance to, oh my goodness. And the uncertainties, I'll come back to it, may be a little better, it may be a little worse, it may be a lot worse. Okay. But, and this is where it gets fantastic, humans have looked for things to burn to give us energy for a very, very long time. We're the first generation in history that knows that we can build a sustainable energy system that will power us and our kids and our grandkids and their grandkids and their grandkids. We're the first generation in history that knows we can do this. And if you were to go through the 15,000 pages of IPCC or the National Academy or the Royal Society or of all these others, and you were to pull it into a tweet, it might look something like this. Compared to business as usual, if we use our knowledge on climate and energy, we get a bigger economy, we get more jobs, we get greater national security, we get improved health and a cleaner environment, which is more consistent with the Golden Rule. That is a vast amount of scholarship that I can't go through, but that's the summary. Using our knowledge with respect and commitment makes us better off. Okay? So I'm now going to, for the next 15 minutes, focus on a little piece of this very big story. So I'm going to say a little bit about climate history. And what it does in the end is it allows us to say that, of course, Gavin's right. He's going to talk about models, strengths and weaknesses and what have you. But when we look, do the models work in really different places and times? They actually do pretty well, okay? So what do we do in paleoclimate? We go back and we find records of past climate changes. We find records of things that might have caused it. Volcanoes blocking the sun changing, what have you. Something that changed is changeable. We should understand that. If things change together, that doesn't tell us who caused what, but it's sure interesting and we should understand it. Okay? And then when we have these histories of what changed and what might have changed, we do hypothesis testing. What will the next sample, what will the next measurement that we've never done before show? If we understand this, we should predict the next one, and we do, and that works. And then we can use these to test the models, and they work pretty well, okay? So that's what we do. So a few pictures. When I was younger, I used to put on big boots and get on big planes, and we'd go up in the middle of Greenland. We're on 2 miles of ice. We are 200 miles from the nearest rock. It is a fascinating place if you ever get up there. It's sort of cold and windy. We were up there, and this fox came trotting into camp. Beautiful, beautiful creature. This is the 4th of July. If you're up there for the 4th, you have to celebrate, and you might even get some freeze-dried laundry, you know, right? When I took this picture, we had been there a month, okay? The newspaper was actually a month old. We had no resupply. But a month-old newspaper is actually perfectly functional. Right, and I labeled this a good day in Greenland. This is a bad day in Greenland. The newspaper is right there. What can we say? Okay, so what are we doing? We were drilling ice cores. 2 miles of ice have been piling up. There's a record in that. And so here, big boots, we had T-shirts made, big boots, big science, right? So there's Catherine from Alaska up on the drill. And here's Bill Kimball from New Hampshire. We're down in an under snow laboratory. That's an ice core. And this one's from 1,547 meters depth. We're a mile down. We're headed down through history. Wanda Kapsner here, Kurt Cuffey looking at an ice core. What is Kurt looking at? It's sort of like this. And so this is 1,411.8 meters, 1,411.9. Here's a winter, here's a summer, here's a winter, here's a summer, here's a winter. I spent several years of my life working with a lot of other people around the world to be able to say that with a completely straight face and high confidence. That this really is a winter, summer, winter, summer, winter. We do know that. And once we have that, with a little knowledge of ice flow, the thickness of an annual layer is how much it snowed. And if you know how much snow is coming, you can learn what was in the air. Dust and sea salt and pollution from, we can see the plumbum from Roman plumbing mining. And micrometeorites from space and odd isotopes made by cosmic rays. If it's in the air, it's in the ice. And we can tell how it changes over time. Okay, so that's really, really wonderful. We have several ways that I could go into later on how we reconstruct the temperature, and there are bubbles in there that are samples of old air. And we've got them all together, okay? So we do that, and then there's lots more. So I got to help a little bit. You can look at this picture from East Greenland. This is a glacier. It used to be here. If you're up front and you're really good, you will see little lines along the hillside where it was 12,000 years ago. And here's Tom Lowell from Cincinnati, and he is about to ask this boulder how much of a cosmic ray burn it has. When the glacier dug it up and put it on the surface, it started getting damaged by cosmic rays, and he's going to ask it how big the cosmic ray burn is, how long has it been sitting there since the ice moved. Okay? Now, these are old beaches. They just look like beaches, except they're not down at the coast anymore. And here's Philip Conkling and George Denton, and you can date these. So here's Brenda Hall from Maine. This is an 8,000-year-old scallop. Scallops don't live in Greenland anymore, so Brenda is doing history, both when and what. And so we start putting these, this is permafrost. If you go to Greenland, this is what the landscape looks like. That's active permafrost. If you hike the Appalachian Trail in Pennsylvania, you say bad words because you twist your ankle on the rocks that got there when it was permafrost during the Ice Age. And it's not permafrost anymore, but it was, and here's Pennsylvania and here's Greenland, right? And so we put this together, working with lots and lots of other people around the world, and what do we find? And here's the really, this is CSI Greenland, really short. I'm teaching a course in this, and this is a whole semester on this slide, okay? So when the sun changes, the temperature changes. The sun doesn't change much very fast. If it did, we'd be in a different world, but it doesn't. It's very faithful up there, okay? Big volcano explodes, it blocks the sun, it gets cold the next year. There's no way for a volcano in Indonesia to call up a volcano in Alaska and say, on 3, let's erupt. And as a consequence, they just make noise, okay? I have spent a lot of my career looking for weirdness. The magnetic field zeroed out, the cosmic rays came streaming in, the climate ignored it. Okay, the meteorite killed the dinosaurs, but not much sense, okay? The ocean circulation really does matter. Its interactions with sea ice, there's some really crazy jumps. Changes in sunshine from the Earth's orbit really do matter, but greenhouse gases matter a lot. CO2 is a big deal. And so there's lots of ways to change the climate, some that don't, but CO2's in there, right? Now, way back, I was down on the tip of the Antarctic Peninsula. This is a Jurassic fern fossil from Antarctica. Yeah, the climate has changed a lot. And there's fantastic people who are doing work older than anything I've done. People here at the Smithsonian, people elsewhere. This was a National Science Foundation project a few years ago. And when you look farther back, this is now 400 million years. 400 million years ago is over here, today is over there. These are various estimates of CO2. The meeting tomorrow is going to discuss, they're already better than this plot, and they will get better. But the broad picture is pretty good. This is when there's ice on Earth. CO2 is high, no ice. CO2 is low, ice. CO2 is high, no ice. CO2 is low, ice. And we do know the direction of causation here. It is primarily from CO2 to ice, not the other way. Okay, so this is here. We have ice ages over here because the CO2 fell for natural reasons, but very slowly. Okay, that's 100 million years. We're a little faster than that. I'm going to take you right down to a little spike over here. There's a lot of work Scott Wing does here, others at the Smithsonian, and other people here, Jim Zakos and others work on this. 55.9 million years ago, nature released CO2. About as much as we humans might if we keep burning. We're doing it faster and faster is harder. So this is not as big a test for nature as a burn it all future for us would be. But what did this easier test do? Well, on land, pretty much everything that lived moved or died. And the big critters got little. We're big critters, so that's a little worrisome. Either it was too hot for them or they couldn't get enough nutrition, loss of soil fertility, insect damage to leaves, a bunch of other things. Pretty much everything changed. In the ocean, it got hot and things migrate and there's some extinctions on the seafloor and you lose reefs as viable ecosystems that build things and, a little bit of hydrogen sulfide coming out. This is a big deal, but not as big as what we might do. It's also not as big as what nature has done. This is a trackway from the Grand Canyon in the Permian. At the end of the Permian, there was this vast volcanic outpouring. One volcano puts out a little bit of CO2 and a bunch of particles that block the sun and makes it colder. But then the particles fall down and the CO2 stays up. And if you have enough volcanoes, eventually the CO2 starts building up. And then it starts reacting with the volcanic rock and fertilizing the ocean. And then if it's too much, crazy things happen. And this big outpouring of CO2 from volcanoes killed most of the known species on Earth. And the ocean is running out of oxygen and it's belching out hydrogen sulfide and it's getting so hot in the tropics that it looks like it was too hot in the tropics for big animals at all. Okay. All right. So what do we know? Climate changes for many reasons. And it has changed throughout history, but CO2 has been especially important. Climate change affected living things. We often first saw something happen to life, and then later we realized it was climate. Okay? A lot of CO2, nature will take it out in 500,000 years. Kill a lot of creatures, nature will reproduce, will give us new biodiversity in a few million or a few tens of millions of years. Life goes on. It's going to go on. But if you're worried about us, or the things here with us, 500,000 years to pull out the CO2 and millions of years to reproduce biodiversity is a long time, right? Paleoclimate says, hey, when they run the models for the past, it looks pretty good. They actually do work pretty well if there's a problem. It's that the world changes a little more and a little faster than the models. But I think that's the debate. I don't think I would say there's a problem. I would say we could have a debate about whether we're being a little bit too optimistic or not. But not much debate about whether we're being too scary or not. Okay. Now, just a word about ice ages. So here's a picture. This is a digital elevation model that Tom Lowell gave me. And you see where you are. There's Lake Michigan, and there's Indiana. And these are the footprints of an ice sheet, right? And the ice was down here, and then it wobbled back, and it wobbled back, and it wobbled back. At some point, it was there, and it went away. And we had these, first because CO2 fell over millions and millions and millions of years, and then because features of Earth's orbit moved the sunshine around. But that affected CO2, which made it a global thing. And so it starts with CO2, it is paced by Earth's orbit, but it's globalized by CO2. Climate changes for many reasons, but CO2 is important. And when the ice sat here, the ocean was 400 feet lower. And here's the Chesapeake, you're right there. And when the ocean was 400 feet lower, this was just a river valley. You can see the old river valley in there. And when the ice melted because of sun and CO2, the ocean came up 400 feet and they gave us the modern Chesapeake. Right? Now, there's still enough ice left to raise sea level 200 feet. We are expecting, by the time our students are old, something like 2 feet, maybe less if we slow down the warming, maybe more if we speed it up. And people often quote an uncertainty of 1 foot or 3 feet, but there's 200 on, and some of it might collapse fast. And we might expect 1 or 3 and get 15. And this business on the uncertainties, it could be a little better, it could be a little worse, it could be a lot worse if we ignore our science and don't use our knowledge. That's the distribution, okay? This is a fire in Los Angeles. The hills around Los Angeles have always burned. That means that they're burnable. And that means that when this is a human-set fire, no one would ever say the hills have always burned, so humans can't burn it. The climate has always changed. Climate is changeable. Climate change has always affected living things, so climate change is important. Climate has changed for many reasons, but especially CO2, so our CO2 is especially important. Okay? And if we use our knowledge from this and from energy and from the whole picture, we end up better off. Thank you.
So, I've never followed Richard before. It's daunting, but I shall do my best. Okay. So I'm going to try and look backward, but very much in order to look forward. This is where we started. This is my ex-boss, Jim Hansen. Some of you might recognize him. 1988 was the first time that he said, in a congressional hearing, that global warming was here and that it had been detected and that meant it was going to get worse. At the time, 1988 was the warmest year on record. And this is the temperatures that we've seen since then. That warmest year on record now is not even in the top 20 years. The 2016 was the warmest, 2017 a close second behind it. But we obviously have more information. It goes back not just to here, to the 19th century, but back even further. We have information about temperature changes on Earth. But how big are these changes? Are they important? Right? I think Richard gave you a sense of that. But let's put it in another way. So the change since the 19th century is about 2 degrees Fahrenheit. So the temperature in this room here, because of our 100 watts that we're giving out all the time, the temperature here is going to increase by about 2 degrees Fahrenheit while we're sitting here. And I'm hopefully none of you are going to become extinct and the chairs aren't melting and nothing terrible is going to happen. But what's the scale for the planet? How cold was the planet during the last ice age, the maximum of the last ice age? It turns out it was only about 8 or 9 degrees Fahrenheit cooler than it was in the pre-industrial. So if we think about these things in terms of that scaling, right, this is about a quarter of an ice age that we have warmed the planet. And where we're going under a devil may care scenario is about 1 whole ice age unit by the end of the century. And the ice age was a very, very different time, as Richard gave you, I think, that impression. Another ice age unit in the other direction will also be a very different kind of place. But you don't need data to see how much has changed. You can go anywhere where there's been ice. Right? This is a photograph from the Mendenhall Glacier in Alaska, taken in 1894. You can go to that exact same spot right now, and what does it look like? Right. I love the way that people will viscerally react to those photographs when nobody looks at the data on the graph and takes a deep breath, right? But you see the before and after, you go, right? How information gets processed is very important. This is the key, though, right? How do we make predictions? If we had observations of the future, we obviously would trust them more than models, right? But unfortunately, observations of the future are not available at this time, right? And That's the crux, right? In order to make predictions, in order to use our information that we've gained from the universe, from our work on physics and chemistry and all the rest of it, we need to have models that can make predictions and that are credible. This is a model. Some of you might recognize what kind of model this is. This is a very old model. It's written in Fortran, which we still use. Thankfully, we no longer use punch cards, but this is one of our early climate models. Just to point out that we have been working on climate models for over 40 years. The processes that a climate model has to capture, though, range over 14 orders of magnitude, which is massive, right? So from the tiniest little smallest particle that goes to make a nucleating particle in a cloud, all the way to the size of the planet, is like 14 powers of 10. That's massive. There's no single theory that covers all of that. In time as well, you go from microseconds out to millennia. Again, 14 powers of 10. Right? You remember that old movie? That's a lot of different scales. And there are lots and lots of processes that we need to understand. We need to understand the formation and impact of sea ice in the Arctic, clouds everywhere, radiation coming from the sun, radiation going from the planet out to space. We need to understand all of those different interactions. And each of them makes up a piece of the jigsaw that is the climate system. We don't know everything. So as we put all of these bits together, we end up with something that looks very much like the planet, but we know it's incomplete. We know there are things that we haven't included. We know that we've put in things that are a little bit wrong. But the basic patterns that we see in these models are recognizable as being related to our Earth. This is a model simulation. What you're seeing, the different colors, is the composition of the atmosphere. The orange coming off the Sahara is dust. Right? The blue swirling in the storms in the North Atlantic is sea salt that's being whipped up by the winds and the waves. The red dots are fires that are giving off the green that you can see, which is organics, black carbon, organic aerosols and the like. The white wispy stuff that you can see in India and in China, that's sulfate pollution. You get that from burning dirty coal, and we're burning a lot of dirty coal. What you can see is that each of those components is being pushed around by the weather and by the climate system. But because they're having an impact on clouds and rainfall and radiation, they are affecting the climate as well. And so the whole thing is a dance where everything is feeding back on everything else. It's enormously complex, but yet it's recognizable as the patterns that we see in satellites all the time. Richard gave you a list of some of the reasons why climate changes, and I have the same list, pretty much. so what was in the Earth's orbit? The sun, volcanoes, you mentioned all of those, right? Fires, you didn't mention that one, that's a big one. The ozone hole, that's changed the climate, but only recently. Deforestation changes the climate, contrails change the climate, and of course greenhouse gases change the climate. There have been many, many reasons for the climate to change. And so when you think about attribution of any particular change, you have to do that CSI exercise. You look for all the suspects and you try and eliminate the ones that don't fit. We test our models to demonstrate whether they're skillful. We know that they're wrong, right? So the question that people ask about models, oh, your model isn't right. And I say, yes, of course it's not right. You know, if it was as complex as the real world, it would be as big as the real world. So obviously it's simpler than the real world and therefore it's wrong. But the question that you have to ask of a model is whether it is useful. Does it provide skillful predictions of something that you wouldn't otherwise have been able to say? Weather forecasts are skillful and getting more and more skillful because our understanding of the processes is increasing. A 3-day forecast now is as good as a 1-day forecast was 20 years ago. A 5-day forecast is as good as a 3-day forecast used to be. And now 10-day forecasts, some of the times, are actually skillful. Don't go any further than that, though. Right? If somebody asks you to buy a 60-day forecast, you just walk away. We can test our models with all the things that have happened over the 20th century. And over the 20th century, there was a lot of noise, there was a lot of weather, there was a lot of El Niños and things. But by the end of the 20th century, you see something different emerge. This is the model. This is the observation, slightly smooth, so you can see these patterns come out more clearly. You see something happening in the 1980s, and in the 1990s, and in the 2000s, and in the 2010s. You see a new pattern emerging. And we can go back and we can ask, hey model, why did you get that pattern? Where did that come from? And it came from the human contributions to climate change. Greenhouse gases, aerosols, deforestation. We can tell how skillful the models are in respect to smaller things, right? So there was a big eruption in the Philippines in 1991, June 1991, right? That put so much stuff into the stratosphere above all of the weather that it affected the climate for years afterwards, right? This is the stuff that was in the atmosphere, and you can see it kind of decayed away, and it was all gone by about 1994. That changed the energy balance of the planet. Because those things were reflective, the sun's radiation came in and was reflected out. And so the net amount of energy coming into the system was less. Right? So that's what that next graph shows. What happens if you take away energy out of the system? It's going to get colder. It did get colder. And in fact, it got colder at exactly the right level that the models predicted, ahead of time. The first model runs were done by October of that year and predicted exactly how much cooling there would be in the subsequent 2 or 3 years. Model forecasts have been successful. We've been doing this for more than 30 years. In 1981, my group, obviously not me, I was still in high school, made predictions of how climate would change over the next 30 years. So they underestimated how much it would change. In 1988, the first transient climate simulation was run to predict what was going to happen over the next 30 years. The models were skillful. In 2005, we did it in a much more sophisticated way with many more contributions from all over the world. And again, the models were skillful. And we did it again in 2011. It's a little bit harder to tell, but again, the models have been skillful. And we're about to start it all over again. And I'm pretty confident that this time around as well, in 20 years' time, you will go back and say, oh yes, the models were skillful. I'm not sure how much comfort that will be at that point. So what might the future look like? Right? We're not soothsayers. We don't know how the economy is going to change. We don't know what technology is going to do. We don't know if we're going to have a war or some kind of other kind of existential crisis. But these are 3 possibilities. This one down here, the business as usual, that's basically the burn it all and don't give a damn scenario. Right? That's what could happen if we really don't pay any attention to this. This one here, aggressive mitigation, that's kind of what we would need to do to kind of stay within the parameters set by the Paris Accord. Right? So that's a global change of about 2 degrees over the pre-industrial. And that's something that might actually happen. What are these numbers? Right, 4 degrees C, I should have changed them to Fahrenheit, I apologize. It's about 8 to 9 Fahrenheit, right? So everywhere that's red there, and the average is about 4 degrees here, that's your one ice age, right? This is incompatible with sea ice of any note in the Arctic. You can see how red Greenland is. It's compatible with a very large amount of melt coming from Greenland, and in fact you can see Antarctica as well. The red that you see over the US is the equivalent of moving the climates of every town or city in the US south, maybe 2,000, 3,000 miles. Yeah, that's like Chicago in Texas. Even this, the aggressive mitigation, there's still warming here. You can't see it. It's about half as much as there. This will still require adapting to. And this is something that we may end up with. Again, not compatible with sea ice in the summer in the Arctic, and compatible with, as yet, an undetermined amount of sea level rise. How do we know that that's credible? It's such a large change. It's outside of the sample that we have trained our models on. It's a massive perturbation. We turn to paleoclimate. Now, back in the 18th century, people were a little bit more, I don't know, wordy. So James Hutton, when he was writing about this, he says, from what has actually been, we have the data for concluding with regard to that which is to happen thereafter. Okay. By the 1980s, we're a little bit better with the pithy soundbite. That's basically the same thing. Back to the future, right? We look back in order to tell us what's going to happen. And we can do it in all sorts of interesting ways, right? This is just a random thing that we did. All the red dots there are the ratio of how much warmer it is on the land compared to the ocean in the future warming scenarios. So, we've doubled carbon dioxide, we've quadrupled carbon dioxide, it's warm, right? And you can see they all kind of fall on a line. That's interesting. And then all these blue dots are where we've tried to model what happened in the last ice age. So it's all much colder, right? With a whole bunch of different models. And interestingly enough, they all line up. And that says that we've found a property of the climate system that is robust to whether it gets colder or whether it gets warmer. And then we can say, but what does the data say? What actually happened during that ice age? And it turns out that we know what happened during that ice age. And it falls right on the line that the models suggest it will. And so we can go back in time and evaluate and validate the results of these models to make better predictions for what's going to happen in the future. We can have more fun. There was a massive lake burst 8,000 years ago. So as the ice was retreating, there was a lake that formed at the edge of the ice that was prevented from going to the north because there was so much ice. And you can still see the shoreline of that lake kind of in Manitoba and Ontario. This is the greatest of the Great Lakes. The amount of water in this lake was equivalent to about 1.5 feet of global sea level rise. Right? That's a lot of water. And when the ice melted, and it was like a dam breaking, that lake drained in about 6 months. So you have a massive amount of fresh water that drained into the Hudson Bay and drained into the North Atlantic, where it had this really odd effect on the ocean circulation. And you can see it in the cores that Richard worked on in Greenland. You can see this spike. Nothing happens in the entirety of the Holocene, pretty much, except this one thing 8,200 years ago. It's measured in isotopes. Well, isotopes aren't a thing that you normally put in a model, but we understand the physics. We can put that in. It's measured in dust concentrations. Well, we have been putting dust in the model, right? You saw the simulation earlier on. We've got dust in the model. You can measure it in methane. Well, we've got methane in the model as well. We can do this. You can measure it in the cosmic ray isotopes that, again, Richard mentioned that you can measure in these ice cores. And we've put those into the model as well. And so you end up using the model and using the physics and the chemistry and everything we've put into those models to evaluate our skill at reproducing something that happened 8,000 years ago. And the funny thing is, it works. It predicts the right sign and magnitude of all of those variables. And the way that it does that is that it changes the circulation in the North Atlantic. Everything cools down for a little bit. There's changes in rainfall, changes in circulation, and the model captures almost all of it. The key thing to remember, though, is that it doesn't matter how far back in time you go, there are no analogs for where we're going. But there may be some clues. Thank you very much.
I've never followed Gavin Schmidt, so I shall try to do my best. First thing is I'd like to remind you guys we're going to be passing out papers where you can write down questions for Gavin and Richard, and they're going to be filtered by some of the top climate scientists at the Smithsonian, unlike the comments on Smithsonian.com. So, very good. If we could just get you guys to work for us, that'd be great. I'd like to start just by zooming out for a minute and recognizing that the things that we're talking about are extremely vast and very unwieldy. We're asking you not only to go back hundreds of millions of years in time, become a time traveler, but also to put yourself in orbit around our planet and think about the whole climate system working. And that's it's kind of a lot to ask. That's a lot to put your mind around. Fortunately for us, we have two people who have spent years and years trying to understand and think about these systems. And unlike the majority of scientists, have spent just as long trying to communicate them to the public through newspaper editorials, TED Talks, PBS series, and realclimate.org.
Books, coffee table books.
Books, also.
With pictures.
Are there any films yet? Hollywood films?
Working on it.
And lots of good pictures of penguins and really good GIFs of climate models. So thank you for not cloning yourselves, or I'd be out of a job. But yeah, so I'd like to ask you to continue the work that you've done, kind of bridging two worlds, communicating your research to the public, and bridge these two worlds. So first I was going to start with, you got to this synergy near the end of your talk, Gavin, but why is it so important for paleoclimate data and all of those troves of data from around the world to talk to the models? And I was going to make you interpretive dance, but I'll just have you talk.
Okay. The key thing to realize is that the things that we're measuring in paleoclimate, whether it's isotopes in ice cores or faunal abundances in ocean sediment or geochemical proxies, they're not what you generally think of as weather variables, right? So if you take the weather model, there isn't an isotope module, there's temperature and rainfall and snow and winds. And those are what we think of as the climate. But it turns out that all these other systems that are the ones that are recorded in these different archives on the ice, in the ocean, in corals, in caves, and the rest of it, they're measuring something else. And in some times and in some places, there's an easy one-to-one correspondence between whatever it is you're measuring and the climate variable that we care about now. But in most other cases, it's actually much more complicated. And it turns out that you need to have an understanding of how these signals are recorded. And then you embed that understanding in the models themselves, so that when you get a fingerprint of change that's in water isotopes, or that's in methane, or that's in foram abundances, you can actually model that directly. And that takes a lot of time and effort to bring the people that know about these systems, which includes the paleo people, but people who are studying it, in the modern world as well, to talk to the modelers, to make sure that these things are embedded in a way that's coherent with all the other things that are going on. And then you can actually compare like with like, which is the most important thing that you should be doing.
And Richard?
Yeah, I mean, it's fantastic. There's an old Calvin and Hobbes cartoon. Some of you may have enough gray hair to remember Calvin and Hobbes. And they're driving along, and they pass a bridge, and it has a sign on it that says load limit 10 tons. And Calvin says to his dad, how do they get the load limit on the bridge? And his dad says, well, they drive bigger and bigger trucks over it until it breaks, and then they rebuild the bridge, and then right? But you know that the load limit on the bridge was done on a model. And when we were in school, at least when I was in school, he's a little younger. When I was in school, the model was probably this is an arch and this is a plate and this is a beam. And we know a lot about arches and plates and beams, and we'll add them up. And I had a slide rule when I started doing this, and then I programmed on punch cards too. But your bridge was designed on a model. Your plane was designed on a model. Your car was designed on a model. Your cell phone was designed on a model. And they work because what science has always done is find the rules. F equals ma, PV equals nRT. And then somebody says, but make it useful. Make it work for me. And we can call that applied science, we could call it engineering, we could call it what is one, but that's a model. And science is never useful until it's put in a model. And it just happens that these guys have built some of the most fantastic models in terms of complexity and the things that have gone into them. And once you build a model, one of the things you have to do is test it. And you want to test it outside of your normal use. You don't want to use every bit of data than your strength of materials in designing that bridge, because if somebody drives a truck over that's a little too heavy, you want to know what'll happen. So you've got to test it outside of what you can calibrate easily. Yeah. And so what we give them history, and they can test against something more. And like I say, the modeling is fantastic, but you will meet people who say, oh, it's just a model. And they drive over bridges. And you should remember that.
And are we seeing more of these two communities talking, data people and modelers?
I think we are. I think that the modelers, the best of the modelers have always known, and the best of the data people have always known, and I think it's diffusing.
So, I mean, in terms of the sociology of science, you're always going to have people that really only want to do their own little thing. And then there are other people who want to have their thing be part of a larger thing. And it's more a question of temperament than it is speciality. So whenever we've kind of incorporated some whole new thing into the model, we generally have a meeting, we invite all these people to come by, and half of them, they tell us all the wonderful things that they're doing, and then at the end we say, well, how are we going to incorporate this into what we're doing? And half of them say, no, our stuff is so complicated and wonderful that you can't possibly do it. And then the other half say, no, I think I see a way of doing it. And we generally talk to those people. But it's a very common pattern. But these climate models are a little bit like the Borg. Eventually all of your sciences will be assimilated. and for some people that's a problem. Other people, they like being part of something bigger. Click. Okay. Yeah. That was the right thing to say. So yes. Questions.
Thank you so much. One of the fun things about writing about climate science for me is talking about the methods and the really creative ways that you go back in time, whether it's fossilized pack rat poop or tree rings or the ice cores you were showing. So why is it important for you, Richard, to show not just what we know, but how we know it? So you always do a really nice job of showing how the science gets done.
Yeah, so partly, be honest, partly this is just a little bit of us trying to show off, because we really love what we do, and it's fun. An ice core is really neat, and we cut thin sections and we put them in cross polars, and they're beautiful, and when we're done with that, we sort of like to show off, and we do. But more and more, I did not go into this to influence energy policy, right? I went into this because I was having fun collecting rocks. But we do produce results that come out into the real world and that matter. And there's a lot of people who have never taken an ice core. There's a lot of people who don't even know a scientist. And so to be able to explain why is it that what we're doing is trustworthy. And engineers worry about this, scientists worry about this, people with virtually any of you have expertise in something. And somebody will say, you're an expert, I trust you, and somebody else will say, why should I trust you? And the ability to be able to explain, this is what I do, and this is how I know it works. It matters as much to a firefighter as it does to a scientist, as it does to an engineer, as it does to a modeler, as it does to a chef. And, and we are in particular in a field that if you're a magician, you don't always show what you did. But we take pride in showing what we did and making sure somebody can duplicate it. So yeah, it's a little showing off, but a whole lot of it is because through no fault of our own, what we do really does matter out in the bigger world. and we've got to make that accessible.
Yeah. And do you also spend a lot of time showing not just what the models are doing, but how you got them and all the factors that went into them?
Not quite so much. It's a lot easier to show pictures of people doing field work.
Right.
My toilet will beat your computer.
Good thing.
The aesthetic joy of seeing somebody squinting at a small screen late night trying to debug their code is not high. But your points are all very well taken. It's very easy to rail against information that just seems to have appeared out of nowhere. It's a very different thing to realize that there's a human being that took that data, that counted those layers, that counted those forams, that lost a finger because of frostbite, or that fell down into a crevasse, or fell off a volcano. These are real people going out into very difficult conditions to get unique data that will not be there for very much longer in many cases, and that's. These guys are heroes, and the women and the men and the children. I guess not the children, but it's a whole community of people who some of them get to hang out on tropical islands and core fossil corals, and that looks like a lot more fun than sitting on summit for 3 months. But it's a human endeavor. One thing that kind of came from what you said a little bit earlier on is, because it's a human endeavor, it's imperfect. Bridges sometimes do collapse. Buildings do burn down. Scientific results are sometimes wrong. One of the things that we have to do in being transparent, in being open, in showing your workings, is that it allows other people to check what is going on, and to make sure that you haven't made a mistake, and to make sure that the bridge is going to fit between the struts, and it isn't going to fall apart the 5 days after you put it in place, right? We do make mistakes as a species, and we have to build in the fact that we're imperfect into everything that we do. And so that means we check it. There isn't just one climate model around the world giving these results. There's 50. There isn't just one ice core, there are many. And in fact, even your project, there was another ice core that was doing exactly the same thing 30 kilometers down the road, if there were any roads, right? Because replication and checking to make sure that you're doing the right thing is absolutely fundamental to science. And it's absolutely fundamental to building the credibility of science, especially if we're going to act on it to do something big with energy or the economy.
Right. And Gavin and his lab have been really in the forefront of leading the transparency on this. And you can see an amazing amount of data and models and other things that they have made available for everybody to look at.
And I'll just ask one more question, then we'll go to the audience ones. But I think hopefully I emphasized how unique both of you are in that you're two of the top climate communicators, not just climate scientists, in the world. And my question was whether you think more scientists should be doing the kind of work you're doing as well on top of their day job, or if not, who should be filling that gap between, I think as you put it, Gavin, the scientific journals and the news headlines besides us?
Right. So I think more people could do more, and what we see there, there's a big shift generationally. The people that are in our lab who are in their 50s and 60s, there are some people that love going to their high schools and church groups and talking about this, and there's other people who you never want to put within 100 miles of a journalist. But the people that we're hiring now, early career researchers, almost every one of them has a Facebook account, wants to run a podcast, is tweeting, is doing this, is writing, so it's a very much a shift generationally. But I run a lab. There's 150 people in my lab. I would say 20 people have like a kind of active communication role at some level, and maybe 6 of them are any good. So that seems like a reasonable ratio. I don't think we want everybody to be doing everything, but the people that are good should be encouraged to do it, and in doing so, they will get better, and that's important for the next generation too.
I talk to scientists all day, and that ratio checks out.
Yeah, I mean, be honest, right? To be a scientist, you have to care deeply and passionately about something for like 5 or 7 years. And then you come out the other end and someone says, okay, now care about people. And we do, we do, but you do have to sort of focus on the stuff. Surveys repeatedly show that if you ask U.S. citizens, do you know a living scientist, that the vast majority do not. It is way easier to dismiss things from people that you don't know. It is way easier to demonize someone as the evil climate scientist who's trying to steal my pickup truck if you don't know the climate scientist. It's really, really hard to look at Gavin and say, wow, you're an evil guy trying to steal my pickup truck.
I don't know.
I wouldn't have anywhere to park it. I live in New York.
and so the business of, we should talk to people. And even if we're not very good at it, we should talk to people and at least let them see what we do and how hard we work and how much we care about it.
Yep.
Putting a face on climate science.
And all science.
All
where the heck did your cell phone come from? Right? I have a different talk I do on what is really a cell phone, right? It's a little sand, a little oil, and the right rocks. And Albert Einstein and Niels Bohr in there, right?
So we're going to go to a couple audience questions. We have one for Gavin. That's what emergent climate or weather behavior have the models successfully predicted that most surprised or impressed you?
Oh, that's a good one.
Yeah, these are pretty good. Some smart people must have filtered these.
Like it's a quality audience, the Smithsonian, right? Yes. So one of the things that I do the most of is looking for interesting things that happened in the past where we can find an interesting test of the models. Like, so this lake in Manitoba and Hudson Bay, like before we did those experiments, nobody had done them. And nobody really thought, well, the models, they're sluggish, they're this, they're that, they're wrong, blah, blah. And they worked. And as somebody who's written the code, and I know that there are errors in the code, and there's comments in the code saying, what is this line even doing? And I've seen the sausage being made, and when you do that, and you make a number of things that you just have to decide to do in order to make it work. And then when they give skillful results of something that's just totally out of the box, you go, oh my God, maybe we actually know something. And it's inevitable a delight when that happens, even if the consequences are not brilliant. But the discovery that we've been able to wrestle something out of the universe, encapsulate it however imperfectly, and have it be skillful is magic. No, well, science, but not magic.
But it almost looks like, right? I mean, they never go into the model and say, wow, we need a Gulf Stream. They go into the model and say, follow physics on the Earth, and a Gulf Stream happens because it has to, because it follows physics on the Earth. And that's really, you get westerlies, and you get easterlies, and you get ITCZs, not because somebody said, program an ITCZ in there, right, but because it has to.
Yes. I mean, like you saw in the animation I gave, there were tropical cyclones that just emerged. There's not something that says, do a tropical cyclone and make it do this. It just emerges as a function of the dynamics, the rotation, the heat in the atmosphere, the stability. It just happens. And we try and make it happen because we know that these things happen in the real world. And so we try and look for the things that are the ingredients, and we try and make sure those ingredients are there. But when they appear and when they actually end up looking like what the distribution in the real world is, it's impressive.
So real magic then. I think you hit on something, Gavin, that I was trying to articulate, that you've seen the sausage being made. So you're not just very good at communicating the climate, but you both have worked doing this research enough that when you say, I'm very confident that this model is skillful, Like, I kind of believe it. It's very authoritative. I have a technical question. Is there a correlation between CO2 increase in atmosphere and O2 decrease? And what is the causation? For example, acidification of oceans causing decrease in photosynthesis.
Yeah. Yes, there is a correlation, and it's burning, right? So you take C out of coal, and you add O2 from the air, and you make CO2, and there's a little less oxygen, and there's a little more CO2 in the atmosphere. There's actually a number of these tracers that one uses that give us very, very high confidence that the rise in CO2 is primarily from burning of fossil fuels. And that includes, there's some isotopic ones. Fossil fuels have no carbon-14 because they're very old and it's all decayed. Plants have carbon-14. We're losing carbon-14 in the CO2 because the rising CO2 is from long dead things. The carbon-13 to carbon-12 ratio of volcanoes is different than the carbon-12 to carbon-13 ratio of living and dead plants. And the change in CO2 in the atmosphere is from living or dead plants because we can see it's not a volcanic ratio. And so we know from the 12 to 13 that it is plants, not volcanoes. We know from 14 that it is long dead plants. And we know from the drop in oxygen that goes with the rise of CO2 that is burning. So we know that the change in CO2 in the atmosphere comes from burning of long dead plants. You can fill it in.
Proof done.
Then you do the bookkeeping and it says the same thing. So yeah.
People worry about the fact that oxygen is going down, but there's so much more oxygen than there is carbon dioxide that while it's a detectable decrease, it's still a very, very small decrease given how much oxygen there is. So we're not going to run out of oxygen anytime soon.
I have another tag team question. Do cores from, I think it's cores from the ocean floor, contribute to the models and the analysis that we have?
Are you?
So the data from those cores are exactly the kinds of things that we use as targets to understand whether we've got the last ice age right. So we have lots of ice age cores, mud from the last ice age that has chemical signatures, geochemical signatures that we try and match with these models. So yeah, so they're a fundamental part of what we're doing. And we have ocean core sediment that goes back. I think there's a little bit that dates back to the Jurassic. It's like 170 million years ago. But we have cores from all over the world that go back to that period, 55 million years ago that you mentioned, or the Cretaceous and the big impact for the dinosaurs. And we can see all of these events in multiple cores around the world. So yeah, they're a big source of the information that we have about the deeper time.
Yeah, Gavin had a blue cross on one plot up there down in the Ice Age, and that's a lot of person years.
Synthesis.
Synthesis, yeah, absolutely. Yes.
Yeah, so people go down to the bottom of the ocean and get a core.
Well, I don't think the people go. We have drills. We have boats that float on the, and then but the drills go down a massive way. I mean, there's some people here who are involved in the ocean drilling program, and I'm amazed. You're drilling in kilometers of water, and you're drilling a kilometer into the mud. I mean, it's a really impressive technological feat.
And what they measure is just fantastic. So if you're a bug in the ocean and you have a cell wall to keep the outside out and the inside in, if it gets too warm, you get really floppy. And so you change the molecules in your cell wall to make it a little stiffer. And because they're cell wall molecules, you make them really, really, really sturdy, and they fall to the bottom of the mud, and you can pull them out later, and you can date them, and you can ask how warm was it when you grow based on the ratio of single to double bonds of carbon in a 37 carbon chain alkenone, because the bug is fixing the plastic in its cell wall to keep its insides proper. And then you can ask the carbon isotopes how much CO2 was in your environment when you did this. And if that isn't fantastic, I don't know what is.
I was wondering, on Smithsonian.com, I've become very familiar with climate misconceptions and misunderstandings. Do you have a favorite myth or misunderstanding? This is your time to lay it to rest forever, both of you.
Well, I mean, the one people will routinely say, climate has always changed, so we shouldn't worry. Can you imagine a person saying, the hills around Los Angeles have always burned, so we're going to disband the arson squad? Is it conceivable that anyone would say people have always died, so that couldn't have been a murder?
Such a good metaphor.
Climate has always changed, so climate is changeable. Now we should understand, what is nature doing, what are humans doing? 100 years ago, nature tried to warm it a little. In the last 30 years, nature tried to cool it off a little. And those first really high numbers that Gavin showed coming off after Jim Henson's testimony are at a time that nature was trying to take it the other way. Right? So climate has always changed. Climate's changeable. Climate change has always affected living things. Climate change is important. CO2 is the biggest thing. We should understand it.
Yeah.
It's very succinct. Yes. And Gavin.
So I've been chasing scientific misconceptions on this for 20 years, and the more that I do it, the more I realize that arguing about specific cliched misconceptions is really not the point. The biggest point is that people don't really understand how science works. They don't get how reproducibility of results is key. They don't get how how science is always kind of the best working hypothesis right now and can be improved. And as it gets improved, it's not a sign of weakness that something gets corrected for a mistake that was made, or for a data problem that we've only just recognized. It's a strength that we're making things progressively better. And so it's the real fundamental disconnect between the way that you use a model in science, in the same way that you use a model to build a bridge. The science is the model, right? Without the models, there's no science. Without the ability to predict, and you need a model to predict anything, then you're not really doing science. And so, this notion that people sometimes say, "Oh, well, that's just a model result." No, that's a scientific result. And so I spend a lot more time now trying to talk about how science works, who does science, how you check science, how you build credibility. These models are not credible because they're complex. They're complex because that was needed to make them credible. And so we sometimes throw too much stuff at people, and they get the impression that just because we've worked on it for a long time, that it therefore must be good. No, we've worked on it a long time because it's good, and we keep on doing it. And so that kind of the backwards logic is actually the biggest misconception I come across, and it's underneath a lot of the other kind of more obvious, kind of classic misconceptions.
Yeah, and we talked about this a little bit before, that people think either that there's a eureka moment and science happens, or that a new finding overturns some entire foundation that we had, whereas really it's usually tweaking or adding to, or just reconfiguring. Yeah, we deal with that as well.
Yeah, I mean the metaphor that so some people think that science is a house of cards, and one little piece goes away and the whole thing collapses. But it's not. It's actually kind of like a ziggurat, and it's been built up on layers and layers and layers and layers and layers. And the science that we're doing now, we're basically, arguing about, what color the interior wallpaper should be in the top floor bathroom.
That's great. So much better than adjusting the chairs in the Titanic, too. Very good. I'm using that imagery. This question's kind of general, I think, about what this program is about. So most of the public is not aware how much the climate has changed in the past, so how dramatic it's been, that long tail. So what are strategies you use to educate people more effectively on our long history of change, for both of you?
Anything and everything, right? So it is. This long story is just so fascinating. and who lived where and what they did. And I love it, and I guarantee there are people sitting out here who have written this story who desperately love it. And it gives us insight to where we are and to what the future might hold. And so I think part of it is share the excitement, you know. And I think it's, I'll be honest, personally, it's really hard to go next door and walk through the fossils and not be excited, right? And you're doing better things even now. So it is really tell the stories, right? People identify with stories. Let's tell the stories. What did we learn? What happened? How did we get here? Where is it going? And share some of just how much fun it is. And come on. You work for the Smithsonian.
You're preaching to the choir.
I'm preaching to the,
You're speaking
great,
my language.
Right? We subscribe, right? So, yeah.
Thank you. We need that.
I mean, people respond to things that are in their daily life, and you know, I mean, I live in New York City. You know, a lot of people spend a lot of time in Central Park. You can see the tracks of the glaciers and the rocks in Central Park. You can see, if you go to Brooklyn, you can see the terminal moraine of that whole last ice age glacier that stretched from Prospect Park in Brooklyn all the way to the Arctic Circle. And you can see the evidence right in front of you. And if you go back, you know, the cliffs of the Palisades going up along the Hudson, you know, that dates from, is it one of the big igneous intrusions that actually was part of one of these previous massive climate events. And so the evidence of this past change is right now where we are. And sometimes if we kind of pull ourselves out of our daily commute or the school run or the, you know, going shopping, and then actually look around us and see how it got to be the way it is, then, you know, our little problems and our issues can sometimes be a little bit minimized compared to the scale of the things that the planet has seen.
Taking the long view. Yeah, so I have one. A lot of these questions are about how you deal with scientists who don't agree with the data, or people who won't listen to it. But I think you've kind of addressed how you handle misconceptions about how science works. So this one is more about how you communicate. In presenting scientific information about climate change, do you take into account the psychological effect on people? For instance, we know that gloom and doom shuts people down, motivated avoidance. So do you work to be optimistic? Do you strive to be objective?
So there's a little bit of a myth, I think, that, you know, scientists are supposed to be totally objective and not have feelings and not care about what they do. That's a total myth. And sometimes scientists kind of play into it because they think it's like a higher status thing to be totally objective. But I think that's actually problematic, because when you are doing things that do make a difference, people think it's odd that you don't care. People will think it's odd that a doctor, you know, who's studying lung cancer wouldn't care about their patients smoking. It's odd for scientists studying climate not to care about where we're going. You know, like a couple of years ago, when, you know, we were going into that warmest year, 2016, I predicted, you know, like after January, that year would be the warmest year on record. And as the data came in, and at the end of the year, yes, it was the warmest year on record. And I'm kind of like, I'm split in two. You know, my intellectual scientist side is going, yes, I made a prediction. Yes, I understood something. I got it right. Yes, ha.
Oh crap, I was right.
And then the other part, like the sane part, says, oh, shit, I didn't want that to happen. I don't want it to get warmer. I don't want our predictions to come true. And, you know, we're not the first generation of scientists or the only science for which this happens, but it isn't sufficient. And so, you know, Sherwood Rowland, who won the Nobel Prize for coming up with the chemistry that explained ozone depletion, and he said many years afterwards, you know, what's the good of having developed a science well enough to make successful predictions if in the end all you're going to do is sit around and wait for them to come true. And that's the dilemma that we have. You know, we're all human, and we care, hopefully, about other people and our families and our children and the generations to come, and we don't want these things to happen. And if we pretend that we're totally neutral about whether it happens or not, it's not truthful. It's not sincere. And was it Groucho Marx that said that sincerity is everything? If you can fake that, you've got it made.
Oscar Wilde,
Maybe Oscar Wilde.
Oscar
You
Wilde.
know,
I'll look it up though.
somebody famous.
I'll have to fact check
no
that.
doubt. Yes.
But you also, yes. My last slide, if we use our knowledge, we end up better off. And that is the difference between your various ones up there. If you couple that to an economic model and you ask, so how well do we do economically if we let warming run amok versus if we tune the system, and we always end up with a bigger economy. Across all the economy, I believe everything now agrees it's serious, that taking this in count in our planning in the broadest sense gives a better economy. And that, we're weeds. Humans are the greatest weed ever. We will muddle through somehow. But there's a lot of people out there that we can help if we can make this knowledge be useful in a good way. And we really do. There's a different thread in this wonderful, horrible story of humans trying to get that energy, trying to get our 100 serfs to do our business, and burning everything we could get our hands on, running out and suffering the consequences. And whenever we ran out, the one I often point to, when the pilgrims get to Cape Cod, it is goodly wooded to the shore. In the late 1600s, the town of Eastham outlaws your own ability to cut your own tree on your own property because deforestation had become so extreme that they didn't know what to do for fuel, and the government got in people's faces because when there's scarcity, that's what happens. And eventually, they were using trees to boil salt water to get salt to pack cod to ship to England for trade goods. And eventually they switched to renewables, and they used windmills and solar drying troughs to get their salt, and eventually they let the trees grow back. Right? We can use this knowledge.
I really appreciate that. It's a really nice way to put it. It's not about being optimistic or pessimistic. It's about looking at the possibilities and saying that there are bright possibilities as well. Human innovation. So I think we're just about out of time here. But thank you so much for enriching the public discussion as you do through so many mediums. Let's have a round of applause.
Thank you very much.
Thank you. It's really an honor to be up here. And as you were saying, Richard, I think now for the first time we're being able to see climate models from the 80s and 90s come true, unfortunately and fortunately. And the next step is making better models that predict farther out, and it's just these kinds of conversations, Freudian slip, that help do that and help us figure out how to act on them. So thank you so much, and thanks all for spending a beautiful evening with us.
Thank you.
Thank you.